Almost 90% of Ugandan youths can ride a bicycle. Amazing. Welcome to Easy Science International and greetings from Ivan. In this video, we are going to look at the action spectrum. In our previous video, we looked at that. This is the graph showing the amount of light absorbed by a given photosynthetic pigment at different wavelengths. To our beloved subscribers, feel free to leave a comment in the comment box below. That can be in form of a suggestion, question, or correction. Yes. Then to our beloved fresh viewers, endeavor to subscribe to Easy Science International such that I send you notifications whenever I release brand new videos. The action spectrum. By definition, this is a graph showing the relative effectiveness of the different wavelengths of light in stimulating the rate of photosynthesis. Let us take an analogy of Chameleon riding a bicycle. Amidst this pandemic, since private cars are not allowed to be drove. The bicycle I'm talking about now is not this usual changer where a Chameleon can change the gears, but it is the typical MANYI KIFUBA or the ILO type of bicycle, where for Chameleon we must employ energy on the pedals, hence riding the bicycle. So the lower the energy Chameleon uses in pedaling, the lower the acceleration of Chameleon's bicycle. Therefore, using more energy increases the rate of pedaling, which in turn increases the acceleration of Chameleon's bicycle. Now, applying this analogy of the bicycle to the action spectrum, let us take the acceleration of Chameleon's bicycle to be the rate of photosynthesis, and the energy which Chameleon uses in pedaling the bicycle to be the light energy, and the varying energy which Chameleon uses in pedaling the bicycle to be the varying wavelengths of light. Let us take the topography of the ground where Chameleon is riding the bicycle to be the chlorophyll air molecule. Therefore, using more energy increases the rate of pedaling, which in turn increases the acceleration of Chameleon's bicycle. So this is our action spectrum. It is a sketch. We see that on the y-axis we have the rate of photosynthesis, and then on the x-axis we have the wavelength in nanometers. Therefore, when we look at this, it goes from 400 nanometers, that is from violet, indigo, blue, green, yellow, orange, red, up to 700 nanometers, that is red. Now, we see that for the action spectrum, the wavelength of light which are very effective at stimulating the rate of photosynthesis are the blue to violet range. They are very effective. As you can see, the graph is very up like this. Then also we see that in the red range here. Now, from green, yellow, and orange, these wavelengths of light are less effective in simulating the rate of photosynthesis. Therefore, when we liken this to Chameleon's bicycle, we see that these two regions simulate the experience of Chameleon riding a bicycle down a hill. Whereas here, it represents an experience of Chameleon riding a bicycle up a hill. So basically this is the action spectrum, and when you look, you must sketch it where the wavelength in nanometers, these are the units, and then here we have the rate of photosynthesis in arbitrary units. That is in arbitrary units. Yes. So we see that we make 3 observations here, to be precise. The first observation is the violet, indigo, blue range and the red range are the most effective wavelengths in stimulating the rate of photosynthesis. Then the green, yellow and orange range are less effective in stimulating the rate of photosynthesis. We also observe that the violet, indigo and the blue range of the action spectrum or wavelength are more effective in stimulating the rate of photosynthesis as compared to the red range. That is because of the I peak here. That is because of the higher maximum here as compared to that one. Yes. So thank you for listening.